Hello everybody and welcome to the 13th appointment. Hopefully it's not for bad luck, number 13 in Italian. It's something which is not really a good wish. But anyway, it's material nonlinearity, and this is by far the most complicated nonlinearity which we can find, due also to the fact that it's not easy to get the material nonlinear properties, or at least not for all of them. So we start with again a very simple example: a beam undergoing pure bending, and we use nonlinear elastic perfectly plastic material, which means that we have a linear behavior up to the yield limit and then a constant stress while the strain is still increasing. So here it's treated in a way to get 50% of the section which is totally plastified. Residual stresses also is shown how they can come out, deformation and residual deformation as well. Then we switch to the theoretical case of 100% of the section which is totally 100% is totally plastified, which will generate here this continuity that the FE model won't be able really to catch. So having exactly something like that. In the end, Latin said that natura non facit saltus, meaning that it cannot be discontinued, so there will be somehow a continuity between the two parts of the section under tension and compression. Then the example is repeated with 3D elements. These were plane stress elements. This is then repeated to see that we get very similar results. Then a similar approach with the same material is done for a round bar under pure torsion, so 50% of the section totally plastified, residual stresses and displacement and strains. And then we use these capabilities that we have learned so far to see how it was possible, or how it's generally now done, I think, by all the F1 team, on how to exploit the plastic field of the material to lighten parts. In this case, it's a drive shaft. We model 1/3 of it, just because it's symmetrical. We use anti-symmetrical boundary conditions, because the torque will generate an anti-symmetrical load case. And the behavior of the material is not elastic perfectly plastic, but is a bilinear behavior, meaning that also the plastic range will increase by increasing the strains, will increase the stresses. So we do as usual the theoretical calculation, analytical calculations in the linear field, and then we see what happens if we pre-stress the part up to a certain level. Here I would like to highlight the fact that the model is 1/3, as I said, but we exploited the capability of the post-processor to pattern the solution. So because it is symmetrical, clearly it will generate something which is more easy to see, so to say. So here we go for the first pre-stress. So we plastify the material and then with a higher torque, and then we go down for some cycles with the nominal torque, which is this here, seeing that the part will then assess itself to a new linear range, clearly with a permanent deformation, which can be cancelled out by doing the final machining of the part once the thing has been pre-stressed. And some calculations here are then run to check that in the end the part has a higher coefficient of safety, and it is lighter. Of course, by doing that we have come very close or closer to the ultimate limit, and this means that the thing is more subjected to failure if the nominal loads are overcome, or if some exceptional loads coming to the structure, there will be a less plastic margin to make the part safer, but it's lighter. And here we see just into the thickness how the stress is going. The section, the thin wall section, is completely plastified. And then we come back again on the example of the inlet for the nacelle, engine nacelle of an aircraft. And here we see the submodel, which is superimposed to the global model, sectioned. And again, because of the way the flange connection was done, there was a spacer interposed between the two flanges. This was done to protect the bolt, in the sense that an overload will then tend to plastify this, and to make the bolt a little bit more soft by increasing its length. Clearly this is done to see what happens for an exceptional load case, like it was the fan blade out. So when one of the blade of the compressor is for some reason lost, then there is a rundown which runs clearly unbalanced, and it's generating huge forces on the flange connection. And here we go very deep into details to see what happens to this thing with the nodal stresses and the Gauss stresses that we mentioned in paragraph chapter 3. And then we talk about true stress, true strain, what is the difference between them, and what could be the error which is done using one or the other compared to one or the other. So generally the codes will need to have the true strain, true stress, but generally the data are given in nominal stress and nominal strain. So here it's explained how to pass from one to the other, and it is shown that for a ductile material the difference is bigger than a fragile material between true stress and true strains. And therefore, for this example here, we checked what is the difference between the two, and it's not so much. Then again, we come back to the example which we already discussed in chapter 7 with the advanced linear calculation, and it is put into the nonlinear material approach because we have set the gasket with a nonlinear behavior, elastic plastic behavior, and here the calculation is repeated. No big difference compared to what happens to the bolt between nonlinear calculation and linear calculation, but big difference for what concerns the gasket, that in that case was considered to be clearly linear and with no contacts, and here we have contacts and nonlinear material. And then, which is very new, it's one of the different topics which is new, elastomeric materials, so rubbers in the end, so even if they still maintain a sort of linearity in the sense that when we remove the load, the part will go back to its original shape, they undergo huge deformation. So the constitutive equations are different from one of a metallic material, for example. We don't enter into these details, but we simply show that we need definitely some tests to characterize the rubber, and then we need to find among different models that the codes make available, we need to find what model behavior is fitting at the best the experimental data. And here just a simple example that was already present in chapter 1 as just a picture for axisymmetric elements. This is the case. So we have an O-ring which needs to be fit into the into the housing. This is done with interference, and then the code will solve the interference at the first step, so it will move all the nodes until they come into contact, so it will be this situation in the end. And then this tube will be pressed down to squeeze again the OR. And this is something we can see. As I already mentioned, the description of the pictures which are in blue will have a reference. At the end of the book you can find the URL to get the animation of the corresponding model. And here we see principal stresses, tension, compression, contact pressure, etc. So it's then the working pressure is applied, and again it's changing all the deformations and the situation inside. When we have elastomeric material and we need to go into a 3D model, things starts to be a little bit challenging, because the mesh size needed for the hyperelastic elements is quite fine, and a 3D model will generate a huge number of degrees of freedom, and on top of that the non-linearity due to the huge deformation of the parts will make the thing difficult to solve. But we will see how this problem might be overcome in some cases. And again, that's it for chapter 13. Next one is dynamic analysis, but again we'll deal with that in the next appointment. Ciao!